Good evening, class. We are looking at the exam 4 review, covering Chapter 4, Application of Differentiation, Chapter 5, Integrals, Section 6.1, Areas Between Curves, and here's 5.5, the substitution rule. We're going to continue on that, and areas between curves. Evaluate the integral of ln x to the second power over x dx. In general, when you are integrating and ln x is involved, ln x is a choice option. As you know, its derivative is 1 over x, therefore du is 1 over x dx or dx over x. Both ways are fine. And I'm going to rewrite that so it becomes clear what we are dealing with, which is ln x to the second power, or u squared. 1 over the x dx or dx over x. Both formats are fine. That is du. And now we can use the power rule, 1 over 3 u cubed plus 3. And replace the u with ln x, and you're done. It's important to recognize this as ln x times itself 3 times rather than ln of x cubed, which is a different story. Anytime you have a fractional format, the very first step is to simplify it, put it in lowest term if possible. If not, normally the choice of u is the denominator. Notice the derivative of the bottom is the top. E to the power of x itself plus e to the power minus x is minus e to the power minus x. Therefore, if u is the denominator, du is the numerator times dx. And of course, remember, dx always belongs to the numerator. So I'm going to rewrite it so it becomes clear we are dealing with du over u. And that, we know it's a natural log. Natural log of absolute value of u plus a constant, and we're going to replace the u. And as always, you can differentiate the result, you get this one back. By the way, e to the power of x plus e to the power minus x, it is positive. You could use parentheses instead, and that's fine. So what happens here, we are dealing with a substitution and, of course, a definite integral. How do we evaluate it? First and foremost, this is 25 minus x to the power of 1/2, and we let 25 minus x squared be u. If I differentiate it, I get negative 2x, and therefore du is negative 2x dx. I like to rewrite this so it becomes clear what we are dealing with here. If you look at this one, it's almost looking like du. And by the way, as I've said, in most texts, they solve for dx. I hope you take the easy way out that I'm showing you. Negative 2 is a number, it's missing. You put the negative 2 in, it's reciprocal negative 1/2 out. It's important to know the product must be 1 and the two numbers, and the two must be numbers. So we're going to rewrite this as negative 1/2, the integral of square root of u du. And what are the limits? We're going to discuss that in a moment. For now, I want to finish that. I want to show you that you can always go back to the original variable. So let's write this as u to the power of 1/2. And this we have dealt with a number of times. So negative 1/2 remains. And this one, we follow the power rule. And 1 over 1/2 plus 1, u to the power of 1/2 plus 1. This is 3/2. This is the reciprocal 2/3. The product of these two is negative 1/3. And again, I'm not writing the limits. It's important to know the original limits pertain to original variable x. So we can go back to the original variable and write negative 1/3, 25 minus x squared to the power of 3/2 from 3 to 4 and evaluate. However, what if we want to go with the new limits? All you have to do, replace the 3 here. I hope you see 3 squared is 9. So 25 minus 9 is 16. If you put the 4 here, 4 squared is 16. 25 minus 16 is 9. So those are the new limits. Normally, it's easier to evaluate it with the new limits. Okay, that's why I'm going to stick with that, but nevertheless, both of them will result in the same thing. So plug in the upper limit 9, and then minus plug in the lower limit 16. 9 to the power of 3 halves means the square root of 9 cubed. 16 to the power of 3 halves means square root of 16 cubed. So what do we have here? As you know, this is 3, and cubed is 27. This is 4, cubed is 64, minus gives you negative 37. With negative 1/3 becomes positive 37 thirds. The integral of 0 to 1 ln of x plus 1 over x plus 1 dx, as it was mentioned, when natural log is involved, that is the choice of you. Its derivative is 1 over x plus 1, therefore du is 1 over x plus 1 dx. We are going to rewrite this so it becomes clear that we are dealing with u du. And again, the power rule says it's half of u squared, but you can go back to original variable and original limits, or you can plug in 0 here. You get ln1, which is 0. You put 1, you get ln2. And it's important to keep ln2 as ln2. So you plug in ln2. You plug in 0, doesn't change anything. So half of ln2 quantity squared. Again, don't mix it up with ln of number 2 squared. Those are two different things. This means ln2 times ln2, and that's an exact answer, everybody. All right, we want to evaluate the integrals. This is the integral of negative 2 to 2 parentheses x to the power of 6 plus 1 dx. When we have a function is either odd or even, okay, sometimes it's neither. But when it's odd, okay, integral of symmetric functions, if it's continuous from negative a to a. If f is odd, f of minus x is minus f of x. So if that is the case, the integral of minus a to a f of x dx becomes 0. So take a look at this one. As you can even clearly see from here, this area and this area are identical, but this one is at top considered positive, this one at the bottom negative. They cancel each other. That's why we get 0. But this one, if f is even, the f of minus x equals f of x, the integral of minus a to a f of x dx is 2 times the integral of 0 to a f of x dx. So if it's even, which means, okay, odd means symmetric with respect to the origin. Even means symmetric with respect to the y-axis. So the left and right are identical. The area is the same. So you can evaluate the integral from 0 to a and multiply 0 to a and multiply by 2. Therefore, this one, if we show it's even, and it is, it's easier to evaluate it that way. So the function, this is f of x. And if I replace the x with minus, in other words, f of minus x equals f of x is x to the power of 6 plus 1, because this is minus x to the power of 6 plus 1, which is the same as this one. So we're going to evaluate it from 0 to 2 and then multiply it by 2. One might say, okay, what's the big deal? It's normally a lot easier to evaluate from 0 to 2 than evaluate from negative 2 to 2. Now, this is 1 over 7x to the power of 7. This is plus x. And you plug in 2. 0 gives you 0. Just plug in 2. 2 to the power of 7 is 128 over 7. And of course, 2 is 14 over 7. You add it to 120 and times 2 becomes 284 over 7 times 2 because of this number outside. The point being, I mean, you really don't have to do that, but evaluation from negative 2 to 2, if you put negative 2 to 2 here and you don't have a 2, it takes a little bit longer. The integral of negative 1 to 1 tan x over 1 plus x squared plus x to the power of 4 dx. This is 0. Why is that? You have to prove the function is an odd function. So what is the function? First of all, this is the function. F of x is tan x over 1 plus x squared plus x to the power of 4. Now, if I replace the x with negative x, I hope you see that the bottom doesn't change, but the top becomes tan of minus x, which is minus tan of x. And therefore, we proved, because f of minus x equals minus f of x, the function is an odd function. And because it's an odd function, you don't have to do anything. By the way, this is nearly impossible to calculate its integral. We want to evaluate the integrals, and I want you to notice side by side the two functions involved, trigonometric functions, more specifically sinusoidal functions. So when the argument, in this case, x squared, when the argument has an exponent, that is the choice of u. Its derivative is 2x, therefore du is 2x dx. We will rewrite this. So we bring x next to 2x. Everything is in order except number 2. And again, I emphasize, just a number is missing. Instead, you can solve for dx. Instead, I'm going to multiply by 2, and I'm going to divide by 2. So 2 and 1/2, their product is 1. So it's 1/2 the integral of sine u du. So the derivative of sine is cosine, but the integral is negative. So negative 1/2 cosine u on a constant. And u is replaced by x squared, and we are done. Negative 1/2 cosine of x squared plus c is the final answer. What happens when sine and cosine both are involved? The one that doesn't have an exponent is a choice of u. So in this case, u equals sine x. What is its derivative? Cosine x. What is du? Cosine x dx. So therefore, you're dealing with the integral of u squared du, which uses the easy process of the power rule, 1/3 u cubed plus a constant. Replace the u, 1/3 sine cubed x plus a constant, and you're done. It's that simple, everybody. What about the integral of cosine to the power of 20th x sine x dx? Again, this one has the exponent. Cosine is the choice of u. As you know, its derivative is negative sine, so du becomes negative sine x dx. So, not a big deal. We need negative sine x dx is missing. We put a negative in and out. Take a look. This is cosine to the power of 20. This is sine x dx. I'm going to put a negative sine next to it. I hope you see negative times negative makes it positive. In other words, minus 1 here, minus 1 here, they undo each other. So in essence, you are dealing with the negative integral of u to the power of 20 du, which is negative 1 over 21 u to the power of 21 and a constant. U is replaced by cosine. So negative 1 over 21 cosine to the power of 21x plus a constant. We can model the rate of airflow into the lungs by the function f of t is half of sine of 2 power 5 t liters per second, where t is the time in seconds. Find the total amount of air inhaled in one cycle, known as the tidal volume, if the cycle lasts 5 seconds. It's important to know that it takes 5 seconds to go with in and out. So the time of inhalation is half of the entire cycle. So 5 becomes 5 halves. It's important to know. Total amount of air inhaled is from the integral of 0 to 5 halves f of t dt, and you put the function here. So again, it's the entire cycle, known as tidal volume, takes 5 seconds in and out. So The inhalation is going to take half of it on the average. So to do this, we are going to use the substitution. Notice this is sign of something. Let's call it u. So let u be 2 power over 5t, this one. Its derivative is du dt is 2 power over 5, therefore du is 2 power over 5 dt. So we are going to move things around so it becomes clear what we have, what's missing. So let's write this as 1/2, put it outside. It remains inside or outside, makes no difference. The integral of 0 to 5 halves sine of 2 power over 5t and dt. So when we look at du, we see everything is in order except 2 power over 5 is missing. 2 power over 5, it's important to know it's a number. So I can put 2 power over 5 here. Okay, so if I put that here, how do I undo that? It's reciprocal, 5 over 2 pi. Again, 2 power 5 is a number. You can do that because that's a number, and of course, it's an exact answer. Now, this is 5 over 4 pi. This is sine of u du. So sine of u du. All right, so let's write it. Now, I'm going to go over the limits in a moment. So you have the integral of sine, which is negative cosine. So you get 5 over 4 pi minus cosine u. What are the new limits? Let's find out. If I put the 0 here, I hope you see that. I get 0. 0 gives me 2 pi over 5 times 0. But what if I put 5 halves? I get 2 pi over 5 times t, which is 5 halves, which is just pi. So let's take the negative out. We have cosine of pi minus cosine of 0. And cosine of pi is negative 1 minus cosine of 0 is positive 1. They add up to negative 2. So you have positive 10 over 4 pi or 5 over 2 pi, precisely, roughly 0.796 or 0.80 liters. As far as rough estimate, even this one is rough, class, but it is important to pay attention to the fact that if you are answering it with an approximation, you have to answer it with the number of decimals that they ask you, okay? And we are going to move on, everybody. All right. We want to integrate tan of x. We don't have a formula for it, so we recall that it's sine over cosine. And we also recall if we are dealing with a fraction, first we have to simplify. If we can, the choice of u would be the denominator. In this case is cosine. The derivative is negative sine, which makes the u negative sine x dx. All right. We're going to rewrite it in a fashion that becomes clear what we are dealing with. So we have 1 over cosine x, and then we have sine x dx. Now everything is in order except the negative sign is missing. So if I put a negative in, I put a negative out, and they take care of the business because -1 times -1 is +1. Now I have minus 1 over u du, and we know that's a natural log. So minus natural log of u with plus the constant, and of course, in the absolute value. Replace it. Minus ln of cosine x plus 1. Notice with logarithmic properties, this I can put it as the exponent here. And why do I do that? Cosine x to the power of -1 means 1 over cosine, which is secant. So it's ln of absolute value of secant x plus a constant. That's pretty straightforward, everybody. The area of a region between the two curves, section 6.1. First, recall the area under the curve is exactly the limit as n goes to infinity of summation of I from 1 to n f of x of I delta x, which is the same as the integral of a to b f of x dx. If this is a positive function, it's area under the curve. If it's not, it's the difference of areas, where delta x is b minus a over n, x of I is a plus I delta x. So that's the first thing that I want to remind everybody. And now, so we want okay, let f and g be continuous functions with f of x larger than or equal to g of x over the interval of a to b. In other words, f is large, f is at top of g if you were to graph it in the given interval. Doesn't matter what happens outside that. And then the area of the region between the two curves, this green region area, from x equals a, the vertical line x equals a, and to x equals b, the vertical line x equals b is, here's the area of the region between the two functions, as you can see it from the graph. Here's the area under the function, the top function f of x, this entire. Here's the red one is the area under the region of the smaller function g of x. So clearly, here's the entire green one, here's the red one. If you subtract the red from the green one, you get this top green one. This is the answer. So the integral of a to b f of x minus g of x dx equals the integral of a to b f of x dx. That's what this represents. Minus the integral of a to b g of x dx. So that's very straightforward, and I hope everybody is okay with that. So what is the process? The area of the region between two curves, here's the process. Number one, graph the two functions. Number two, find the points of intersection, set f of x equals g of x, and solve. And then evaluate the integral. So what happens? This strip of a rectangular shape with the height h and the width dh, we're going to call it, okay? It's called the area of a typical rectangle is y of the top minus y of the bottom times delta x or dx. dh becomes dx if you sweep this along the x-axis. If you go this way and that way to cover this area. If you go up and down, becomes dy. Therefore, we write dA is h dh. So a typical rectangle, dA, an increment of area, is h times dh. And the integral of a to b HDH is the actual area. This is an increment of area. And it's either the integral of a to b y of the top minus y of the bottom. T stands for the top, b for the bottom, dx, or x of the right side minus x of the left side, dy from a to b. We will look at a couple of examples to make some sense out of this. So the integral of a to b f of x minus g of x dx. Now find the area of the region bounded by this function y equals to x squared minus 3x plus 2. The x-axis, x equals 0 and x equals 2. First and foremost, I'm going to assume everybody can graph. This is a basic parabola, and all you have to do, pick up a few points, including the vertex, x equals minus b over 2a, and do that. Or even if you use a graphing calculator, it's really not that big of a deal. So you graph it. And we want it from 0 to 2. When we say x equals 0, it's the y-axis. So in essence, we are looking for the following area, everybody. That's what we are looking. And of course, this is the vertex. Again, just reminding you, the x coordinate is minus b over 2a. The y coordinate you plug into the function. So here's a typical increment of an area. Here's the height, and here's the width. Okay. dA is HDH, and this is y of the top minus y of the bottom. That means y of the top minus y of the bottom. And y of the top comes from the function y or f of x, and y of the bottom comes from the x-axis. X-axis has the equation y equals 0, everybody. So this is f minus 0. And this is dx, because we are going to move this along the x-axis. So y of the top comes from the function or the curve or the parabola. Y of the bottom comes from the x-axis. And then dx, because this width is dx or delta x. By the way, this is extremely small. I want you to know that. So that's what we get. Minus 0 has no effect. And so the area is the integral of a to b HDH. So we're going to plug in and evaluate it. So it's important to, let me just erase my work so it becomes clear what's, it's important to understand how we come up with this. So the drawing truly helps, okay? All right, so what is this? 2/3 x cubed minus 3/2 x squared plus 2x from 0 to 2. And you plug in 2 cubed, 8 times 2, 16/3 minus 2 squared is 4 times 3, 12 over 2 is 6, so minus 6 plus 4, and they add up to 10/3. I'm going to, generally speaking, I'm going to just go from here to the answer because this is elementary algebra. I hope everybody can see that. Find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. Remember, y equals x squared opens up, minus x squared opens down, 2 takes it up, and this is just y equals x, a line that goes through the origin. So we are interested in this area. That's really the answer. So we need to find these 2 points. I'm going to erase my work in a moment, but I made it huge, so for the sake of argument. And so the very first step is to understand the typical, and let me erase my work. It becomes, because I want you to pay attention to that. And before I even do that, this is an increment of the area, the typical um, rectangle that moves along the x-axis from left to right to cover the entire area. So that is, and that's why from A to B. Okay. And so having said that, looks like that. This is the shaded region, looks like that. And first, we are setting them equal. Let me erase my work because we want to find points of intersection. So 2 minus x squared equals x. And since we want to solve, and hopefully by factoring, I'm going to move everything to the right side, becomes x squared plus x minus 2. This is easy factoring. You want two numbers, the product is -2, the sum is 1. 2 and minus 1. So x is either -2 or +1. And because g of x equals x, when you put it in, you get -2, -2, and you get 1, 1. And by the way, you really should check with this one just to double check. Okay, but it's easier. I use that one. And so what we are dealing with here, here's the top, here's the bottom. So the height, the top comes from the curve F, the bottom from the line G, so F minus G. Therefore, a typical rectangle dA is y of the top, T stands for the top, minus y of the B, B stands for the bottom, dx, and y of the top, 2 minus x squared, minus y of the bottom, x, and dx. We are going to integrate this from the x squared minus 2 to the x, from the x coordinate minus 2 to the x coordinate 1. By the way, it so happened that y coordinates are the same, but we are going from x to x, okay? Because we are sweeping this across the x-axis. And so this one is 2x minus 1/3 x cubed minus half of x squared from -2 to 1, plug in 1, plug in -2. I leave it for you to evaluate it, and it becomes 9/2. So definitely show that it's equal to 9/2. Now, we want to find the area of the region bounded by the graph of x equals 3 minus y squared and y equals x minus 1. So I hope you remember x equals y squared. It's a parabola opens to the right, minus y squared to the left, 3 minus y squared. Okay. It's a parabola that still opens to the left. Okay. And it's been shifted to the right by 3 units. And y equals x minus 1 is just a line. So this is the parabola. And y equals x minus 1, we graph it, but because this is a function of x, we're going to make this one a function of x also. X equals, I hope you see that you move the -1, y plus 1. And why do we do that? I hope you see the curve. So we want this shaded region. And I hope you see the curve is completely on the right side of the line. Whereas the line is at top of it from here to here, and then over here, right here, if you draw a typical rectangle, the top and the bottom are both coming from the curve. So look at this, and we are going to set them equal to find points of intersection. And again, a typical rectangle goes like this, everybody. So let's set them equal. 3 minus y squared equals y plus 1, because we set the x. We set the x for these two equal. And again, I'm going to move this to the right, becomes y squared plus y plus 1. Subtract 3 becomes -2. So bring everything to the right, and then factor it. Y is either 1 or -2. Now, y is 1. So if I put it here, x becomes 2. We have 2, 1. If I put it here, negative 2 plus 1 becomes negative 1. So negative 1, negative 2. And if I put it here, I can double check my work. Now, here's a typical rectangle. And the height is x of the right minus x of the left. X of the right minus x of the left. So this is g minus f. Okay. And this rectangle, we take it up and down. That's why we have the dy. And the limits are the limits on the y, which is from negative 2 to positive 1 in any event. So g minus f. So we have 3 minus y squared minus y plus 1. So that's dA, x sub r minus x sub left, L dy. And we're going to call him f of y and g of y in an event. And so we are going to integrate this one from the y coordinate negative 2 to the y coordinate 1. And let's say this is minus y squared minus 1 minus 1 minus y minus 1. Let me just write it minus y minus 1. So these two add up. So we have negative y squared minus y plus 2. This gives us negative 1/3 y cubed. This gives us negative 1/2 y squared. This gives us 2y. You have to plug in the upper limit 1, evaluate it. You have to plug in lower limit negative 2, evaluate it. Their difference is 9/2, and you have to show that, everybody. Okay. It's pretty straightforward. A quick recap. The function, and we're going to call this curve f of g of y 3 minus y squared. And the line, we're going to call it f of y plus 1. The curve is completely on the right side of the line from the bottom to the top. That's why we use x sub r minus x sub r minus x sub n for the height. What is the width? dy. So dh becomes dy. dh becomes dy. All right, we want to find the area of the region that is bounded by the graphs of f of x equals 2x plus 1, which is a line, and g of x, which is x squared plus 1, which is, again, a parabola. You know y equals x squared and then moves up by 1. So you're going to graph them, and I'm going to assume that you have no problem graphing the two functions. One of them is a parabola, one of them is a line. So number one, graph them. Number two, going to find point of intersection. In essence, it's given, but let's just see the process. Set f of x equals g of x. So set the two equal. And I can get rid of the 1 and x squared minus 2x. I factor the x out. And x is either 0 or 2. So 0. If I put the 0 here, I get 1. If I put 2 here, I get 5. So those are points of intersection, and I can double check with this guy too. Now we want to evaluate the integral, but we have to know an increment of a volume. And here's the increment from the bottom to top. And the top comes from the line which is y equals 2x plus 1. And the bottom comes from the curve, which is x squared plus 1. And so dA is y of the top minus y of the bottom times dx, because this width is dx. It moves along the x-axis. So the top, 2x plus 1 minus the bottom, x squared plus 1 dx. So that's f minus g. And that's the y of the top minus y of the bottom. We're going to evaluate the integral. We're going to evaluate the integral from the x coordinate 0 to x coordinate 2 of this piece. First, let's simplify by writing this one as minus x squared minus 1, which is 2x minus x squared. Then this is x squared. This is minus 1/3 x cubed from 0 to 2. If you put 0, it goes away. If you put 2, you get 2 squared minus 2 cubed thirds. And this is 4. This is minus 8/3. And it becomes 4/3. 4 minus 8/3. And we're done. What's interesting about this is that you can do a second method, and because as you can see, the line is completely at top of the curve. Also, the curve is completely on the right of the line. So you could look at this and say, now this is x of the right minus x of the left. So h is g minus f. So the curve minus the line, but we have to write both of them as a function of x. So this one is, by the way, f of x, this means y, everybody. This means y, right? This means y. So we're going to solve this one, okay, is y 2x plus 1. This one, y equals x squared plus 1. This one, you move the 1 and divide by 2. This is easy. I want to explain about this one. I hope you see that y equals x squared plus 1. And let me quickly show you this means y minus 1 equals x squared, and x is plus minus the square root of y minus 1. Now, the right half is positive square root of y minus 1. The left half is the negative, and since it's the right half, we write the positive one. And so now we are going to write x sub r minus x sub l times dy and evaluate it from a to b. So the evaluation takes place from 1 to 5, the integral of 1 to 5. Okay, the right side is this one, the square root of 1 minus 1. And the left side is the line half of y minus 1 dy. Let me erase my work. We get this. Now, I hope you see that this, you can use the substitution on that and write it as y minus 1 to the power of 1/2. Okay. And if you call this u equals y minus 1, du is dy. So it's a very simple case of u to the power of 1/2. And we have done that before. So I hope everybody can evaluate this. This becomes 1 over 1/2 plus 1 u to the power of 1/2 plus 1. And eventually it becomes 2/3. This one is just 1/2 of y. So 1/2 times you integrate this. This is half of y squared. This is minus y. In other words, let me erase my work. So this is y minus 1 to the power 1 half, and this is what you get. Now, if you, I'm going to highly recommend you guys do this. You make sure you can go from here to here. Okay, this is actually a good practice for you. And now we want to evaluate it from 1 to 5. So if I put a 5 here, 5 minus 1 is 4. If I put 5 here, 25 halves minus 5. And then I'm going to put 1 here. This becomes 0. And this becomes 1 half minus 1, which is negative 1 half. I want to quickly show you the evaluation. 4 to the power of 3 halves. Square root of 4 is 2. Cubed is 8 times 2 is 16 thirds. 25 halves minus 10 halves. 5 is 10 halves. Is 15 halves. And then negative 1 half makes it minus 15 fourths. This is 0, so it goes away. Negative times negative. Positive 1/4. This makes it negative 1/4. 16 thirds minus 15 fourths. And negative 1/4. It's 16 thirds minus 16 thirds minus 16 fourths, which becomes 16 over 12 or 4 thirds. This is the second method. And not every question can be done by two methods. So I highly recommend you take a look at this one and see how interesting it is that we can do it both ways. You want to find the area of the region between these two curves, and you have to graph them in class. This is a cube function. This is a parabola. So graph the two functions. And this is the cube function. This is the parabola that obviously minus x squared opens down. And so what area are we interested in? This one and this one. Okay. So please understand that at some point in this part, the cube function is at top of the parabola. But in this part is the other way around. So this is what we want. So first, we have to find points of intersection. So it's important to know this is the cube function and this is the parabola. So we write it. Now, we want to set the two equal. 3x cubed minus x squared minus 10x equals minus x squared plus 2x. And you don't have to move this. They're identical. We just drop them. And move this, make it minus 2x. So 3x squared minus 12x. That's, by the way, this is f minus g, okay? There is a reason I wrote that, so because we're going to use that later on. So we need f minus g. 3x times x squared minus 4. As you know, x squared minus 4 is x squared equals 4. This gives you plus minus 2. This gives you 0. So we have 3 answers. And now those are points of intersection. X is minus 2 here. And you can plug it in here or there. It's easier to probably plug it in here. So for example, if you put minus 2, you get positive 4 with negative is negative 4 and negative 4 is. So this point has coordinates negative 2 minus 8. Okay. And you can figure out obviously 0, 0 is easy. And if you plug in 2, this becomes 4, this becomes 4, but this negative makes it minus 4 plus 4, they cancel each other. So this portion, the curve is at top, f is at top, that's why I put f minus g is this, okay? And this portion is a different story. So if you want to evaluate the integral, so dA is y of the top minus y of the bottom times dx in both cases. However, in this case, f is at top. In this case, g is at top. That's all I want you to notice. So in this case, maybe I use a different color. Whereas this case, the curve at top is the parabola. Okay, so that's the difference. So that's why we're going to use absolute value of f of x minus g of x dx as we go from a to b. So here, from -2 to 0, we use f minus g, but from 0 to 2, we're going to use g minus f. So this is f minus g. This one is g minus f. So 3x cubed minus 12x. And then for that part, we use the opposite of that, minus 3x cubed plus 12x from 0 to 2. This is 3/4 x to the power of 4 minus 6x squared from -2 to 0. This is minus 3/4 x to the power of 4 plus 6x squared from 0 to 2. And I'm going to leave it for you to plug in and evaluate and convince yourself. The answer is 24. So a quick recap, everybody. This portion, the cube function is at top. But this portion, it's the other way around. This is for the first part. This is for the second part. And here's the final answer, everybody.